Hi everyone. So I'm Rishi. I'm an undergrad, um, and this is a project I worked on. I started last summer at the LPI with Julie Stopar, and I've been continuing work on it this summer with Mike Zanetti. What I'm about to present to you today is a methodology we developed to constrain impact melt volumes in simple impact craters using topographic data. So impact craters produce impact melt. The pressure and heat of an impact will melt some of the country rock, and this melt will be deposited, some of it inside the crater rim, some of it outside. And in simple craters, often what you'll see is a pond of impact melt, a flat surface, and yeah, and the volume of melt generated could depend on target properties. So it's a useful question to ask, can we get a reliable estimate of what volume of impact melt got generated in that impact crater? And can we get an estimate of that using just remote sensing data, such as imagery and topography? So to zero in a bit on what these estimates are going to look like and how we can test our estimates, we'll consider a couple more facts. So melt ponds in impact craters are going to be a mix of not just melt, but also breccia and some other impact heights. So any estimate that you try to produce on what the volume of a melt pond is going to be an upper bound on the possible amount of melt in that melt pond. Then of the target properties that affect melt generation, porosity is probably the most easily testable one. It's theorized from physics that a more porous material will convert more of the energy from the impact into heat instead of shock waves, and so it'll generate more melt. So naturally, this lends us the hypothesis that the lunar highlands, a more porous terrain, should have craters that generate more melt than those in the Maria. So can we test that? Is more melt generated by those craters? So our methodology is going to be built on the foundation of this pretty nifty tool developed by Francis Baum and Mike Zanetti, first presented at LPSC in 2017. It is the Geologic Event Volume Estimator, GeoEVE. It's an ArcGIS model builder tool that you can install from a zip file, really simple. And it'll let you find geologic feature volume differences from an estimated pre-event surface. You can use it to estimate the volumes of both positive and negative relief features. The flowchart you see on the right there is the back end to this tool, which is kind of complicated, but using the tool is not very complicated. So you, the user, to use this tool, only have to provide a couple things. So you need to provide it a DEM roster of the feature whose volume you're trying to measure and some of the terrain near it. Then the user must define some shapefile polygons. You'll define a shapefile polygon around the feature whose volume you're trying to measure, and then another polygon around an area representative of pre-event topography. You'll specify a number of points that will be randomly sampled off the DEM in the pre-event topography polygon that you specified. And then you specify the order of the polynomial surface that will be fitted to that pre-event topography. So order 1 would be a plane, order 2 would be a paraboloid, and so on. And the algorithm will iterate this estimation. It'll run it multiple times because every time it samples points off that surface, it'll produce a new slightly different estimate. So you tell it how many times to estimate, and it'll produce a distribution of volume estimates using that. So as I alluded to, it takes a cut-fill volume difference between the DEM and the trend roster that's been fitted to the pre-event topography. And it'll output that cut-fill volume to a geodatabase at your specification. So looking at this process more visually and the way we do it for impact craters, it's going to look like this. You'll start by acquiring a DTM of the feature you're looking to measure. It has to be map projected. The tool is sensitive to map projection, so you have to stay wary about that if you're looking at high latitude features. What you see pictured here is Bessarion crater on the near side of the moon. And the DTM is the WAC GLD 100 meter resolution. And the imagery overlaid on it is WAC 100 meter mosaic. We're trying to find the area of the melt pond at the center of this crater. So we define a polygon shapefile around that melt pond. Then we have to define a polygon shapefile around a pre-event surface. So we draw a polygon on the crater walls, since we're taking the crater walls to define the shape of the crater as if the melt were absent. When you run the script, it'll place a scattering of points, of random points on that cloud. It'll make point cloud. And they'll sample the DTM values across that pre-event topography surface. And it'll use those to define the trend of your pre-event surface. And it'll repeatedly resample these points, providing data for a Monte Carlo simulation kind of thing. To those randomly selected points, a trend is fitted. In the GeoEVE tool as it was developed by Francis Baum and Mike Zanetti, this trend is going to be a polynomial surface. And so what we've pictured here is a second order polynomial surface, a paraboloid, fitted to the crater walls. The black and white that you see is the trend roster that's been fitted to those points. And the rainbow is also the trend roster fitted to those points. It's the part of it that is coincident with the melt pond that we specified earlier. And so you take a cut fill between that rainbow section and the DEM values in that area. And taking the cut fill between those two ought to give you some sort of volume estimate for the melt pond. Now, this is repeated many times, and it'll produce a distribution of volume estimates, in fact, that looks something like that chart on the bottom left. That's a binned frequency distribution plot. And it'll tend to have a standard deviation of around 20% of its mean. And what you see on the right there is the trend roster, the paraboloid trend roster fitted to the crater walls, stacked directly on top of the crater DEM. So you might look at that and say, hey, that paraboloid doesn't look like it's fitting the crater really great. You know, it's not very representative of the crater cavity beneath the melt pond. And to that, I'll respond by saying, you're right, a paraboloid isn't the best shape to be doing this with. What we actually want to do is use a hyperboloid. So a pretty great paper from 2013 by John Chapelot found using geometric analysis of shadows in simple impact craters that simple impact craters without interior melt deposits are very well fitted by hyperboloids, shape defined by this equation on the bottom right here. And when craters do have melt deposits, their walls still conform to the hyperboloid, but they'll have a flat pond at the bottom. So on this basis, we believe that taking a cut fill volume between the DEM of the surface and a hyperboloid that's been fitted to the crater walls should give us a melt pond fill volume estimate that's physically reasonable, that's meaningful. So in order to implement this, we had to modify GeoEVE, and we replaced the linear regression of the points on the crater walls with a nonlinear regression fitting a hyperboloid to those points on the walls. And now it produces a trend roster from the hyperboloid equation instead of polynomial surfaces. In fact, the way we modified it, you can modify it easily to fit any 3D surface to the crater wall. Now, when we use hyperboloids, there's an annoying mathematical thing that there's a parameter in the hyperboloid equation that controls how pointy it is, and you can't get that from a regression of the walls. So we specifically use cones in this case, but that can be, we're working on it. We're going to figure out how to better parameterize that curvature value. Now, testing this modification using hyperboloids instead of polynomial surfaces, using hyperboloids gives a tighter distribution of volume estimates So it's a better constraint or approximation of fill volume estimates of the melt ponds in these simple impact craters. So we use this new modification of GeoEVE to measure the fill volumes of melt ponds in simple impact craters in both Maria and Highlands targets. We measured 16 craters, suffering time limitations, this being an undergrad project. And what you've got pictured on the right there, that plot, you have mean volume estimates of the craters on the vertical axis against the diameters of the craters whose melt pond fill volumes are being found on the x-axis. In blue are estimates of the volumes of Highlands craters, and in orange are the volume estimates for craters in the lunar Maria. And comparing the two power curves that fit pretty well to those points, we don't really see a significant appreciable difference in the crater fill volumes between these two targets, which is interesting and warrants discussion. So something to note is that the hyperboloid fit implementation in the code is subject to a couple troubles of its own. It is strangely incompatible with some high-resolution DEMs, such as NAC stereo pairs, which are what we really need in order to apply this technique to smaller craters, to craters smaller than 5 kilometers in diameter. And so that limits our data at that scale. Then also it's important to note that we're finding melt pond fill volumes, but that might not necessarily be very representative of the melt volume, because these melt ponds are also going to include debris that fell in from the crater walls. They might contain major wall slumps, but a savvy user could just draw the polygons to avoid these major slumps and excise them from the region whose volume we're calculating. And they could do the same for other non-melt debris that isn't wall slumps. Nevertheless, that'll interfere with your volume estimates. There's also a whole lot of impact melt that's not going to be inside the pond. There's often a lot of melt outside the crater rim in the ejecta blanket. And there's also some subsurface drainage into the heavily fractured material beneath the crater. So what you got pictured there on the bottom right is sort of a side profile of a crater that had a hyperboloid, or specifically a cone, fitted to it. So crater wall on top, and then the rainbow bit is the trend raster of the cone that was fitted to the walls, extending beneath the melt pond. So it looks a lot more robust than the paraboloid fit. In conclusion, GeoEVE is a volume estimation tool for geologic features in general. And here we've refined it for this particular use case of calculating the fill volumes of melt ponds in simple impact craters. The method that we've developed and presented is still subject to a lot of future refinements. It would be better if we understood the debris contribution in these melt ponds and could maybe be able to say like, oh, this % of the volume is debris and this much is melt. It would also be better if we could parameterize the curvature of the hyperboloid using other data, using melt-free craters, so that we don't have to use a pointy cone fit. And the method that we've shown is also very broadly applicable to any planetary surface. So you don't just have to use this on the moon. It could also apply to surfaces like Mercury or Ceres. And so there's a lot more work that you could do with this. So yeah, in acknowledgement, I carried out this research last summer under the LPI super internship, and this summer I continued it at my own university under the SERP fellowship. And if you want to download the original GeoEVE tool, the one that fits polynomial surfaces, feel free to contact my advisor, Mike Zanetti, at the given email. And I also like to mention that I'm applying for grad school this fall. So tell your friends you saw this brilliant undergrad today. Just let them know. Thanks a bunch. I'll take any questions.
Great. Thank you so much. That was wonderful.
Thank you.
There are currently no questions in the chat for this talk.
Okay, well, I'll ask one. So Rishi, you've spent time looking at these simple craters, and I may have missed it mainly because you had some beautiful graphics. But what size simple craters are your 16 craters so far? Um, because you did mention that the next stereo would be needed for, I believe you said, 5 kilometers or less.
Yeah, yeah. So most of our craters are above 5 kilometers. We did attempt a couple below 5 kilometers, but those are kind of sketchy because they were done using the WAC 100-meter DTM.
I have a question.
Yeah,
Is the tool usable for complex craters yet?
unfortunately not. So the hyperboloid fit that we use to define the extent of the crater cavity beneath the melt pond, that wouldn't really be applicable for complex craters because of all the slumping.
Mm-hmm. Do you know if there's plans to try to make it applicable to that kind of feature?
Not at the instant. Uh, we've been tossing around some ideas on how you would even begin to do that, but you couldn't really physically constrain them.
Mike Zanetti, let me scroll
Yeah.
down. Or did somebody unmute?
I unmuted him.
Okay, perfect.
Hey, Mike.
Yeah. So yeah, just to address that, you know, there's so much that's unknown about what's kind of below a complex crater floor, that, you know, how would you know that you're accurate in your shape fit, right? We've been exploring this tool as a way to also try to get some volume estimates for kind of the fill in transition diameter craters, and it's just yeah, you just end up with huge brackets because you really don't know what's going on beneath the crater floors. Simple craters are the only ones that we can really kind of accurately surmise the what's beneath that, what the shape of the crater is beneath the fill.
Yeah.
If I'm not mistaken, I believe Veronica Bray had a paper. I want to say like 2010, 2012-ish time period, maybe 2009-ish, that did look at trying to estimate at least a complex crater fill, assumed to be impact melt, but of course entrained debris as well. So that's also a potential resource starting point to expand to the larger crater diameters.
One thing that we have tried with the kind of original tool, call it, is fitting a really complicated or really high order polynomial function, and also changing the shapefile mapping for complex craters, where you include the walls of the complex crater and also the central peak, and try to fit a really high order polynomial to kind of get that, call it W shape in 3 dimensions. But again, you don't know what's going on beneath the melt sheet to give it any real credibility.
Sure, I can understand that. Thanks.
But I will give a shameless plug that this does work on pretty much everything else. Also, we did volume estimates for Compton-Belkovich, which is a volcanic complex that are, you know, quite well constrained. Same thing for volume of sinuous rills, and pretty much any positive or negative relief feature you can use this tool, and it's proved very useful, just not in my publication record because I haven't written any of the papers for it.
Paul Schenk has a quick question. What is the fit for the curve that's on the screen? Is it proportional to crater diameter in log log?
Oh, the fit. So the fit on the screen, it's a power law curve.
But
I'm sorry, I'm not
Yeah.
understanding.
he's just asking for what the number is of that power law. Right?
Oh yeah, the number is I don't have it on this slide right now. It's 3.7 to 4.1, I think.
Okay, there's nothing else in the chat for the moment.
Okay, cool.
I'll just chime in. I had pulled up Veronica's paper. I was right that it had to do with volumes, but I was incorrect. It's focused on the volumes of the central features of complex craters. So peak and peak ring materials. But I know that she had a lot of difficulty. I believe she even presented this. It is from 2012, by the way, so my memory is not that terrible. As I had thought. She did present this at one of the Planetary Crater Consortium meetings and had discussed in previous years how difficult it was to derive this. So it's kind of the flip side of the coin. Instead of the positive features, we're trying to get at those negative features below the surface a little bit.
Yeah. Using the original GeoEVE tool, it's pretty easy to find the volumes of positive features. It's actually really straightforward. You could do it in like 20 minutes.
Okay, well, since we do have a couple of minutes left, I will ask you, do you have plans to continue this work, or are you going to be passing it on? Because I know that you're going to be trying to pursue, hopefully, planetary science in graduate school.
Yeah, that's right. I think it really depends who I end up working with and what kind of lab I end up working in. I'm also interested in working with hard rocks, so we'll see where I end up.
Great.
I'm not really sure right now.